Welcome back. In this presentation, we'll do more problems of the analysis in pipe flows. We'll also do a few problems on the design in pipe flows, and then we'll cover some basic piping networks. In the first type of analysis problems, if the velocity through the pipe or the volume flow rate through it is given, the following procedure to calculate the pressure difference or the pressure loss through the pipe is recommended. Calculate the flow velocity if the velocity is not given using the volume flow rate and the diameter of the pipe. Next, calculate the Reynolds number and the roughness factor. Then determine the friction factor from the Moody's chart or from a Colebrook calculator. Once we know the value of F, we can determine the head loss using F, V and L by D. In the second type of analysis problem, pressure drop in a length L of the pipe is given and we need to determine the volume flow rate through that pipe. The pipe geometry is also given. But since we do not know the velocity, we cannot calculate Reynolds number. And therefore, we cannot calculate F directly because the Reynolds number is not known. Recall that in fully developed turbulent flow part of the Moody's chart, the value of F is almost constant for a given value of epsilon by D. Since we know the value of epsilon by D, we have a first estimate of F. With this first estimate of F, we estimate the head loss and using the energy equation, estimate the flow velocity. We calculate the Reynolds number based on this estimate of velocity and improve the estimate of F. We'll repeat the above steps till the estimate of F converges to the required level. We do an example. Obtain the flow rate of water carried by a cast iron pipe of diameter 10 centimeter and length 40 meters when the applied head difference is 2 meters. The head loss is related to the velocity head and the value of friction factor F by the relation HL is equal to F times V square by 2G into L by D. So that we can write V as a square root of twice G head loss times diameter divided by F times L, where F is a function of Reynolds number and epsilon by D. Here in this relation, for V, we know everything except the value of F. So we plug in all those values and we get a relation V is equal to 0.313 divided by square root of F. So this should give you a hint directly. If we start with an estimate of F, we calculate a velocity V. From that velocity V, we calculate the Reynolds number. And once I have Reynolds number and the value of epsilon by D, I get the value of F from a Moody's chart or from a Colebrook calculator. The value of epsilon for the cast iron pipe is 0.15 millimeter, so that the epsilon by D is 0.0015. We start by assuming the flow to be fully turbulent, so that F can be estimated without knowing the value of Reynolds number. From the chart, we enter at 0.0015, the value of epsilon by D, the relative pipe roughness. In this, we get a value of F as 0.021. We start with this value and we calculate V from 0.313 divided by under root f, then RED and do the iteration. So, the first value of f we start is 0.021. The value of V from that formula 0.313 divided by square root of f, we get the value of V to be 2.16 meters per second, from which we calculate Reynolds number as 215991 from Colebrook calculator. Let me try if I can open the Colebrook calculator. So the value of f we get from the calculator is 0.0227. This value can also be obtained from the Moody's chart. The next round we start with this value 0.0227 and we get a value of V as 2.08 and the value of Reynolds number is 207745 and the value of f from this is slightly larger 0.0228 and with this value when you put in there I get velocity as 2.07 and the Reynolds number as 207289, slightly lower, but the value of f is the same at 0.0028. Thus, the value of f has converged and we get the flow velocity 2.07 as an estimate of the flow velocity through the cast iron pipe. The volume flow rate corresponding to this velocity is obtained by multiplying this velocity with the cross-sectional area of the pipe and we get 1.63 into 10 to the minus 2 meter cube per second. Next, we do a design problem. The design problem is one that needs the determination of the pipe diameter to carry a given flow rate with a given head loss. And it is rather cumbersome as the unknown diameter d occurs in both the ordinate of the Moody's chart and in the parameter epsilon by d. It is useful to eliminate velocity of the flow from the parameters and express the variables of the Moody's chart in terms of the flow rate q dot, d and HL. Then out of these, q dot and HL are known and d is the unknown. So, the friction factor which is twice HL divided by G V square into d by L becomes pi square G HL divided by 8 q dot square L multiplied by d raised to 5 and from this we can express d like this in terms of q dot and HL. The value of f is not known here, all other quantities are known. And then the Reynolds number can be expressed as 4 rho q dot divided by pi d mu. The following iterative procedure can be used. Since we have no idea where to start, pick any value as an initial guess for f. A value of 0.03 in the middle of the range of f is a good starting point. Estimate d from the given value of q dot, L and HL from the formula for the diameter that we just derived, and then estimate Reynolds number. Once we know d, we can calculate epsilon by d, and using the estimated value of Reynolds number and epsilon by d, we can look up a new estimate of f from the Moody's chart and iterate till the required convergence is obtained. We'll show this process through an example. It is desired to deliver 60 cubic meter per hour of water through a horizontal cast iron pipe. Estimate the pipe diameter that will cause the pressure to drop at 400 Pascal per meter of pipe length. The pressure drop for the pipe of length L is given by this formula, and replacing V average by Q dot. V average is Q dot divided by the area of the pipe, which is pi by 4 d square. We get delta P in terms of Q dot, D and F. And we plug in the value of the known quantities. I get delta P is equal to F times 0.225 L divided by d raised to power 5. For the given value of the parameters, d raised to power 5 can be written as 5.63 into 10 raised to minus 4 divided by F. And Reynolds number can be written as this. So now we are ready to start iteration. We start iteration assuming the value of F as 0.03, Calculate the diameter D, calculate the value of epsilon by D and RED, estimate a new value of F from the Moody's chart or from the Colebrook calculator, and repeat till the required convergence is achieved. So we start from F is equal to 0.03, and we get F from calculator as 0.03280. These calculations can be done very easily on a spreadsheet like Excel with formula embedded, so that the repeated calculation do not take much time. Then using this value in the second iteration, we get a new value as 0.3376. Value F is increasing. I plug in this value next, and I get the value as 0.03408. It is not converged yet. And if I do this 2 more times, I get the converged value of F as 0.03417. And then this is the converged diameter of the required pipe. That is, we need a pipe of 16.5 millimeter diameter to carry the required flow with the given pressure drop.